39 is another situation where we want to use the ratio test because of the factorial and the exponential terms. Right? So when we take the limit as n approaches infinity, our n plus 1th term will be n plus 4 factorial over 3 factorial times n plus 1 factorial times 3 to the n plus 1. We're going to divide that by the nth term, which is the same thing as multiplying by its reciprocal, 3 factorial times n factorial times 3 to the n, all over n plus 3 factorial. All right, so doing some rewrites, as far as n plus 4, we know that's n plus 4 times n plus 3 factorial. We know n plus 1 factorial is n plus 1 times n factorial. And we know that 3 to the n plus 1 is the same thing as 3 to the n times 3. This allows us to cross out a lot of material. We've got the n plus 3 factorials that are gone. We've got the 3 factorials which are gone. We've got the n factorials which are gone, and we have the 3 to the n's which are gone. This leaves us with the limit as n approaches infinity. In the numerator we have n plus 4. Everything else has been eliminated. In the denominator we have a 3 and an n plus 1. So we have 3 times the quantity n plus 1. This limit is equal to 1/3, because our leading coefficients are 1 over 3. And that value is less than 1. So by the ratio test, we know this series converges. Number 40 is very much like the example that I did on the board when we first talked about the ratio test, except we have, instead of 3 to the n and 5 to the n, we have 2 to the n and 3 to the n. This series, again, ratio test is the way to go. Take a look at the other video if you want, because it's the same idea. We're going to end up with a situation where the series will converge because the 3 to the n is more dominant than the 2 to the n. On that same line, now we've got the 3 to the n for 41 that's up in the numerator. So again, if we look at the ratio test, then we're looking at the limit as n approaches infinity. We've got 3 to the n plus 1 over n plus 1 cubed times 2 to the n plus 1. And we're going to multiply that by the reciprocal of the original function, so that's n, or original expression rather, n cubed times 2 to the n over 3 to the n. All right, you're old pros at this by now. This is 3 to the n times 3. This is 2 to the n times 2. The 2 to the n's go out. The 3 to the n's go out. And we are left with 3n cubed. So we have the limit. Oops, sorry about that. The limit as n approaches infinity, 3n cubed is in the numerator, and 2 times the quantity n plus 1 cubed is in the denominator. All right, so what is this limit equal to? Well, if you're not quite sure what to do with this denominator right here, do it quick. We know that n plus 1 cubed is n plus 1 times n plus 1 times n plus 1. So if we start foiling this out, we know that the lead term is going to be n cubed plus a whole bunch of other junk after it. Well, when we multiply this by 2, we end up having, again, the limit as n approaches infinity. We have 3n cubed, and then this 2 times that n gives us 2n cubed plus some other junk right after it. But more importantly, our leading coefficients are the 3 and the 2. So this limit is going to go to 3/2, which is greater than 1. And the ratio test tells us that if we have a value that's greater than 1, the series diverges. And last but not least, with problem number 42, we are looking at a situation where the limit comparison tests could really help us out here. And the reason why the limit comparison test will work out is because we've got this n squared, so we're thinking maybe p series, but the plus 1 is there, right? And we also have an n in the numerator. Right? Now I know that this n squared root of n is really n to the half. So if we think about what this function's behaving like, it's like we have n to the half, sorry about that, over n squared plus 1. What's the difference between our exponents? Yeah, it's 3/2. So this, I'm going to actually need approximate symbols. This is behaving like 1 over n to the 3/2. So let's compare our general term with this p-series right here. Because I know that this p-series converges since p is greater than 1. So I'm going to take the limit as n approaches infinity, and I've got my original series, n to the 1/2 over n squared plus 1, and I'm going to divide that by the series which I know converges. All right. Now, again, dividing by a fraction means we multiply by the reciprocal. So we have n to the 3/2 over 1. Now that can go away. All right, and now if I simplify this expression, I have the limit as n approaches infinity, n to the 3/2 and n to the 1/2 multiply to n to the 4/2, because we add the exponents. 4/2 is 2, so we have n squared. And then in the denominator we have n squared plus 1. This limit is equal to 1. Now, if this was a ratio test, or because the limit's 1, the test would be inconclusive. All right? But we're interested in the limit comparison test. And the limit comparison test is, as long as you get some value c which is greater than 0, then that means that both series either converge or diverge. Again, we know that our series that we compared it with is a convergent series by the p-series test. So that means that our series that we're interested in, root n over n squared plus 1, also converges.